Okay, so I've changed my notes on this since last time I taught chemistry. So a couple of you guys printed off my old version. I've updated these, and one of the reasons why I've updated this is that although the curriculum in your textbook has some information in it, um, a lot has changed, especially in the last couple of years in Canada regarding this next topic here. And I actually find this one particularly fascinating because it really combines the chemistry with a lot of politics. And I'd like to start with that because this today's topic is we got to talk about refining and using crude oil. And I've actually thrown the outcome directly out of the program of studies I'm supposed to teach you. It says you guys are supposed to be able to describe in general terms the physical, chemical, and technological processes used to then separate organic compounds from natural mixtures and solutions. Basically, long story short, we're going to talk about how we take oil out of the ground and how we do stuff with it. And maybe some of you know kind of where I'm going with this is that this has really changed in the last couple of years. Do you guys follow the news a lot and know what's really big even in the last couple of months? Not even that. The pipeline to BC right now is like, I mean, I don't want to get into big politics because I'm not really meaning to be divisive like this, but like, especially right now, Alberta and British Columbia are going through one of the most tumultuous times. I mean, I'm 33. I'm not exactly that old, but I've ever remember, where basically provinces are actually like doing battle against each other economically. You guys hear about the whole how Alberta like put barriers so that like BC wine wasn't allowed into Alberta? Has anybody heard of this sort of stuff going on in the news? Okay, you guys need to read more news. Okay, because like this is our province here. Okay, let me try to lay the groundwork. I don't want to come off as biased one way or the other, but here's basically the story. Okay, Alberta has oil. We've heard this before, right? Okay, that's the groundwork that everybody knows before. There is a lot of oil in the province of Alberta. Most of it's up north. You're talking in the Grand Prairie and north sort of region of Alberta, right? And oil as an export is very valuable to our province's economy, right? I mean, whether or not you want to get into the environmental side, I want to stay away from that just for now, but there are huge environmental implications, obviously. But Alberta has natural resources that historically we've used, right? And we sell our oil to local Albertans. We sell it abroad. But one of the biggest reasons why Alberta kind of this is important is because Alberta is landlocked. You guys know what that means? It does not touch the ocean, which makes it challenging then to export your product internationally. A lot of the oil actually in Canada, believe it or not, actually comes from other countries. And like the United States, that's one of the reasons why people think that they go to war in the Middle East sometimes is that there's oil there and they want to have influence over that. So that is a big part of Alberta. And I threw up a map on here on another slide. I know you guys don't have this one here, but just to give you guys a little bit of context in case you're not, unless it's something you've never really heard before. Alberta is, let's see, this is probably British Columbia is about roughly like this. There's that little edge that juts out. Alberta's give or take right there. Okay. Right about here, there's a lot of oil. Okay. A lot of oil, a lot of natural gas that wants to get exported. And there are a few main ways that Alberta over the last 5 years or so has been trying to work on to export the oil. Let me show you a few of them. One of them was known as Keystone XL. I'll even write that out here. This isn't going to be on any test, by the way, but it's worth knowing. Keystone XL. Anybody know anything about this pipeline? Yeah. It's supposed to go into the States. It's supposed to run down basically through roughly there. It's supposed to hit up the Gulf of Mexico and head that way. The main idea is that it's supposed to export to the U.S. Now, politics-wise, the United States basically had to work together with Canada to make this project happen. About 3, 4, 5 years ago, something like that, back when Obama was in office, the way the United States works is that they have a House of Representatives, they have a Senate, but they also have a president. Basically, everybody in the U.S. said, sure, we'll build the pipeline, but Obama had a veto. And basically, he said, no, this is not, I mean, for whatever his reasons, basically, he said no, didn't want to have it. Mostly environmental stuff is where that comes in. There's also some people who are like, hey, we shouldn't be taking Canadian oil, we should be making our own. There's that sort of stuff too. But now, recently that has changed with Donald Trump coming into office because Donald Trump basically said, yes, we are going to build this pipeline. That was one of his promises. The weird flip now is that it still is in its challenging stages because now, rather than the Republicans being in power, it's very likely the Democrats are going to be in power in the Congress and in the Senate, and so it still may not end up happening. But that was one main method that was called Keystone XL. Some of you have heard of that before? So, I mean, it is complex stuff, and this has nothing to do with science. It has everything to do with politics. So that was one option. There's another option that recently got shut down, and it was called Energy East. And basically, the idea is that it would send energy this way. Now, this was really big in the news because the mayor of Montreal, very far away ways from Alberta, basically had a huge campaign where he was basically preaching the evils of Alberta oil, basically. And so he was very, very opposed to having this pipeline go through Quebec. But the idea would be that this pipeline would then carry oil and natural gas from Alberta to the eastern part of Canada, because I don't believe it currently does a whole lot. Do you guys know how oil is normally transported in Canada otherwise? By train, yeah. And another thing that happened relatively recently in the news, but it's been a while. It happened in a place called, I can't pronounce it because I'm not French, but it was like Lac Magentic, something like that. Does anybody know what happened there about 3 years ago? It wasn't an oil spill. A train was parked on the top of a hill. The conductor didn't brake it properly. The train then rolled back into the small town in Quebec, and the train basically went big kaboom. Okay, you guys need to read more news because like this is big stuff here. I know it's maybe not something you do a lot of, but that's one of the reasons why I want you guys on Science and Society readings. And so that is one of the biggest advocate reasons for why we want to stop trying to send our oil by train, is that a natural disaster that way could happen. Now, I'm not trying to say that pipelines are perfect environmentally, but I think most evidence usually suggests that it's probably better if you're going to transport oil by a pipeline than by train. There's also another reason why it matters to Albertans, and I think this actually matters to a lot of you guys. What else do we transport by train in Canada? Yeah, our farming type stuff, whatever happens to go there. And my understanding is due to pipeline backups, so many cars of oil are being transported by train that it's actually backing up the delivery of wheat. Is that something that any of you guys are aware of? Okay, never mind then. Anyways, that's what I've heard. So I'm getting off topic. That was the second pipeline possibility. This one has been kiboshed for sure, though I believe that one has basically been taken down. In terms of politically in Canada, we recently changed governments to Justin Trudeau about, 2 years ago? 3 years ago now? Something like that. Trudeau, basically, when he came into office, Stephen Harper's Conservatives basically had a whole bunch of different options on the table. This one here, but none of them had really ever been completed in that sort of way. I believe Trudeau basically said Energy East is really not going to happen. So I have no expectations of that. Another pipeline was meant to go this way, and this one had a lot of promise because it had the least amount of distance to travel, and this was called Northern Gateway. Maybe you've heard of that one before too. Northern Gateway would basically have had a port in Prince Rupert, British Columbia, very, very far north, one of the largest towns that's kind of left way up here, because we're talking like, we're talking like the Yukon is kind of up in this area here, and it's getting really close to Alaska. And so Prince Rupert would have been the port that then would have allowed the oil to then hit up Asian markets, ideally. That one went through a lot of process to try to figure out, and eventually it happened about a year ago. Trudeau's government basically said, no, we're not going to do that one either, I believe. So the one that's really big in the news right now is actually an existing pipeline. And I forget the name of it, but the company that's working on it is, I believe, called Kinder Morgan. It's a US-based petroleum company. You're nodding. Okay, I got it right. And basically it goes from up here, and it lands in about Burnaby, British Columbia, somewhere in that area there. Now, there's actually already a pipeline here. And the plan right now is to twin that pipeline and basically double the expansion. And this has kind of been a compromise for many different reasons. One, we're not building over new territory. There's a lot of things to consider. If you want to build a pipeline that's brand new, you've got to pay farmers to let you use their land. There's always the question of how do you deal with the indigenous people and their territories as well, and try to make it so that everybody's happy. So in terms of this one right here, this one seemed to be the most logical because there's already a pipeline there. We're literally just building one next to it. Okay, this has been super big in the news recently because there's been a ton of protests in Burnaby, British Columbia, where protesters are basically saying we don't want to have more oil getting produced. In fact, two members of parliament, including Elizabeth May, the Green Party member, were actually arrested as part of their protests for violating a court order basically saying to stay away. So, anyways, that's kind of the basic context here. This is super relevant to just Alberta in general because there is a lot of um, jobs at stake here. And I want to make sure that I try to present to you guys the chemistry behind this as to what's happening, but also give you the social context. And I hope I'm not trying to push one political view or another here. You probably know where I stand, but that's not my goal here. But basically, this is kind of where things are at, and it is. I mean, it's all over the news sometimes to the point where like literally BC and Alberta. It was about 2 weeks ago. It was almost like when I have to sit down my kids that are 3 and 5 and basically have mediation. Justin Trudeau, the Prime Minister of Canada, literally had to sit down with the Premier of BC and Alberta, have a sit down and say, guys, stop fighting each other. Because like two provinces are like actively like. So, anyways. In a way, yeah. But it was trade war, which is very, very unusual because usually, although trade wars can happen, like right now, Donald Trump is trying to initiate trade wars with everybody, mostly China. It's very unusual to have trade war within your own country. You know? And so there's a lot of people who, whether they're, I'm not sure whether they're maybe being a little extreme or not, but they actually are concerned about confederation for Canada to some degree and say it's not good, it's not healthy for provinces to be fighting. Is there a chance, kind of like how Quebec once wanted to separate, that other provinces could separate from the country? There's that talk always happens. So, anyways, that's our context here. So now that I've kind of discussed with you guys a little bit of the political implications, maybe you can kind of understand why I've rejigged my notes over the last little while. Because your textbook and the curriculum was written like 10 years ago, but a lot of more recent oil stuff for us is actually like currently happening as we speak. Okay. So the next question then maybe lies in, well, what is the point of exporting all this crude oil? Right? And I mean, I won't lie, most of what we're exporting it for is, I've got this on the slide right here, is for gas. Well, we drive a lot. Well, who drove to school today? Yeah, and me too, right? Like, I mean, to some degree, in Canada, especially with a big country like ours, driving is kind of a fact of life. Right? And I mean, in other places, like if you lived in the lower mainland of British Columbia, or other places where maybe you could walk to work or bike, that might change. But I mean, I can't bike to work. Right? And I know a lot of you guys can't too. And so gasoline is by far the largest thing that we send our oil into. However, it is not the only thing. There are many other things we use oil for. So I want to point out a few of them. A very, very large component is actually jet fuel. It is actually hugely costly to both the environment based on carbon dioxide emissions, as well as just for the amount of fuel it takes to actually fly all the planes that go everywhere. And planes means a couple of different things. Yes, a plane could involve ferrying passengers, but I mean, you guys been to Costco? They have fresh fruit in the middle of the winter. Where are they getting that fresh fruit from? Peru, Colombia, the Philippines. You're getting mangoes from South America in the middle of December. How do we get that here? Well, it could be by ship, but if we're talking fresh fruit and it has a short shelf life, it may also be possibly by plane, right? And so anything that involves transportation, that is a large industry trying to bring things to the other side of the world, right? That's a big part of what needs to happen as well. Another thing that I should point out is that we spend a lot of our energy heating homes, right? And someone mentioned carbon tax. That is obviously a new political implication as well. The idea of trying to encourage people to maybe use a little less energy when they can. But that being said, we live in Canada. We just had one of the worst winters I can remember for the longest time, and we probably need to heat our houses. Right? I can actually still remember a time when Kinsey was born. She was a baby, and our heater blew in the dead middle of wintertime. And I was freaking out going, Melissa was also pregnant too. Kinsey was a little baby. Cammie was inside Melissa, she was pregnant. And our heat went out, and it was like minus 40 outside. And I mean, here I am freaking out going, we need to heat our house, right? And so that is another major thing. So I mean, I had to like suck it up and pay for the electricity guy to come fix my furnace at like 3 in the morning at like $200 an hour or whatever he charged. But that was something that obviously to me was really important, right? So, anyways, heating our homes is something that needs to happen. We actually use some on making our roads, but I want to focus a little bit on this section right here. This is what you guys are going to write your research paper on. Because although, yes, a good chunk of our oil and petroleum products do go towards burning them and combusting them, which is something we're going to talk about, the idea of needing to do combustion for whatever purpose we're discussing. The petrochemical industry makes a ton of plastic. Now, if you look at the way the tree works here, it's only 3% of basically everything, according to at least this diagram. Whether this one's entirely accurate, I don't know, but it's about the right ratio here. And I mean, if you look around this classroom and try to consider what is manufactured as some sort of plastic, there's a lot, right? I mean, as we even look around, probably your binders have some sort of plastic component. The plastic metal-y type stuff that you'd have on like my stapler, the table, the whiteboards, the laminate on my posters, my water bottle, your calculators, your cell phones, right? Like if it is some sort of plasticky type thing, that's not, if it's not metal or wood or something along those lines, it's manufactured. Does that make sense? You know, like our clothing. Man, much of our clothing is made out of, we'll learn about this in our polymer section, but nylon, rayon, polyester. Those are all manufactured from crude oil, actually. You might be wearing oil right now as we speak, which is weird because you don't think of it like that, right? But it's clearly gone through a refining process. Unless you're literally wearing like wool or cotton, yeah, it's probably manufactured in some way. And so what I would like you guys to do, by the way, on your research paper is pick some sort of organic compound. And I'll give you some ones to look at in the future if you want some ideas. And I want you to research the implications as to how it gets processed. How do we make plastic? Whatever it happens to be, whether it's like the shopping bags that you get when you go to Safeway and they give you a bag that they charge you 5 cents for. Whether it's the plastic that's on the back of your cell phone, whether you want to do saran wrap, that's another one. Whether you want to talk about polyester clothing, right? Some of the makeup and cosmetics actually involves that. I think actually, I know I didn't teach you this first lesson, but my very, very first slide in the entire lesson, I should just do it like this. My very first slide here, I don't know their Mike did a lot on this, but I wanted to show you all the things that we use chemicals for. Obviously gasoline, solvents, but like polyester, synthetic sweeteners. You guys know what Splenda is? Yeah, like it's like an artificial sugar, artificial flavoring. Do you guys know like how vanilla gets used in the cooking industry? You can actually make artificial vanilla. Medicine is a huge one. The pharmaceutical industry is massive in that way. And I mean, I'll always reference Breaking Bad just because, Walter White really was anybody watch Breaking Bad? A few of you have, right? Walter White was a chemist. Obviously, he did it for illegal purposes, but like really anyone who works in the drug, hopefully the legal drug industry, right? But like that is a huge component. So if you wanted to, for your research project, pick insulin, because that really matters to you, or penicillin, or even just Tylenol. Melissa, my wife, actually has a firm belief. She figures that which is the one she thinks it was, if aspirin, they use aspirin in the hospital quite a bit. I believe aspirin can be used to help prevent against heart attacks, I understand. She figures that if aspirin had been invented 50 years later or 20 years later, she figures it would have probably been about $10 a tablet instead of like you can buy a whole little container of aspirin for $10 because that's how valuable it is in her industry. That's what the market would pay for it. Fortunately, it was invented 50 years ago, and so now you have the brand name ones. You know how there's the knockoff brand ones now. Because of that, it helps decrease the prices because she figures people would pay through the teeth for those drugs otherwise. They'd have to, and the company could just charge whatever they wanted. Anyways, I'm kind of getting off topic. This is a day that really matters to me, by the way. Like I like talking about this, not because it's on your diploma. Just so you guys are aware, in terms of your tests, you might get one question on this sort of stuff, by the way. And I think I can think of 2 questions in all my years teaching chemistry that I've ever seen on this. Okay, so this is not something that you're going to be tested on, and yet, hopefully you can hear the passion in my voice. This is worthwhile stuff to know because this is our lives. Is that the breakfast card? Does anybody want breakfast? Rebecca's on her way, actually. Yeah, you have a customer today. While we're talking about plastics, even think of the little yogurt container that you're going to eat yogurt out of. Plastic spoon, plastic container. All came from the petrochemical industry. Probably started with some sort of oil that began up north by Fort McMurray. Yep. Thanks, guys. Okay, I should talk for a little bit about. Well, no, I'll get to that at the end because that was the point at the end of my lesson here. Okay. Hopefully, I've impressed on you guys, though, the need that, especially in Alberta, with where we live, but just in general, like we use oil. Maybe not in its oil form, although we do use a lot of it in that sort of form, but it's a big industry. And so, again, I'll go back up to this. I need you guys to know a little bit about some of the processes we use to separate organic compounds, things like how we refine. So I've got a ton of pictures over the next few slides, and what I need to do is I need to explain to you guys some of these terms here. Okay. It's not a massive part of the curriculum. This is actually a really short day in terms of like what's really important. But I got some pictures trying to describe how we will then take oil out of the ground and turn it into something useful. Have I set the stage well? So it took me half an hour to get to that point. So let's get started. The first thing I want you guys to know is something called fractional distillation. When whatever company it is manages to get some crude oil out of the ground, okay, it does not come in like nicely separated out amounts. Okay, imagine that you're like my little kids and they're about to go play with Lego. And we have this big tub of Lego. It's got some like 2 bricks, it's got some 4 bricks, it's got some windows and cars and the little minifigures. My favorite ones are when I buy them like Iron Man ones and Batman ones and princess ones. Side note, my daughter, oh, I love this. Kinsey one day decided to build a car and have all of her princess minifigs rescue the Avengers. I was like, oh. Anyways, because we have Avengers and we have princesses. Anyways, okay. Imagine that you've got all these little pieces, right? And in my big mixed up bin of Lego, they are clearly just one big jumble, right? And when Kinsey wants to play with it, she literally has to go through and pick them out and go, I want one of these and one of these and one of these. Well, that's basically how crude oil works. You have a whole ton of different carbon-based chemicals all in the ground. You might have some CH4s, which you guys know as methane. You might have some C2H6s, which would be ethane. You might have some C7H12s or some C52H100s or some C52H102s. And all of that is all jumbled together. Does that make sense? Now, when we want to use this crude oil for various different things, we'd like to have just pure methane or pure ethane, or when you guys go to fill up your tanks with gas, you guys know what gas is actually? Octane. 8 in a row. Right? So you'd like to have just one or the other, right? So in the same way that Kinsey needs to then filter out her Lego blocks, we need to find a way to filter out our petrochemicals. And so the basic idea is that we filter them out based on weight. Okay? In the same way that Kinsey would then take all of the little 1x1 Legos out and the 2x1 Legos out and the 2x2s and all the flat ones, you can filter them based on weight. But more specifically, we're going to filter them out based on boiling point. Okay? Because there's a general rule. The bigger something is as a molecule, the higher the boiling point. And we learned about this last semester. It has to do with something called London forces. I'll even write that down. Do you guys recall the term London forces? Basic concept is that the bigger it is, the higher the boiling point. Basically, the long story short is that the bigger it is, the more electrons it has. The more electrons it has, the more temporary dipoles it can form. And the more temporary dipoles it can form, the more it would stick together. Therefore, it has a higher boiling point. So methane, the smallest of all the hydrocarbons we have, because it's only got 1 carbon, methane is a gas. Now, when you actually put gas in your car, what state of matter is it, though? Yeah, which is like, English is dumb, isn't it? Like, the gas we put in our car is actually a liquid because it's octane, and the reason why is that octane has 8 carbons. That That makes sense? And because it's bigger, it has more London forces, so it sticks together more as a liquid. Right? If we were to upgrade, rather than it being 8 carbons in octane, and upgrade to something that has, like, say, 27 carbons, it's probably now more of like a solid consistency, like what you kind of imagine when you think of like an oily type stuff that's kind of thick, high viscosity kind of thing. Does that make sense? So here's the basic premise. This is known as fractional distillation. What you do is you heat up the crude oil and you boil it. You raise the temperature little by little by little. So you set the temperature, say, to 10 degrees Celsius, and off boils the lowest molecules. The highest ones would come to the top, like, say, well, I should even go higher than that. Like, say, CH4 would come off first. And then you turn the temperature up a little bit more to 20 degrees Celsius. And now the C2H6 boils off. And then you make it 30 degrees Celsius. And now your C8H18, your gasoline, boils off. Does that make sense? And as you increase the temperature, different things boil off, and then you separate it based on boiling point. And so as this, we call this a tower. As the temperature gets increased, the lightest things, they manage to go to the top. And then your things like your greases and your asphalts, things that are obviously very like thick and heavy, well, they don't rise nearly as high. Does that make sense? So very, very clever technique. Fractional distillation is one of the terms I need you guys to know. Does everybody get that one? This is one of 2 questions I can think of ever seeing on a diploma. And basically, I still remember it because, do you guys know who Will Lamb is? Yeah. Graduated years ago. He almost got 100% on his chem diploma, and he got the fractional distillation question wrong because we talked about it afterwards. He felt so silly because the way it works is either the lighter chemicals are on the top and the heavy ones are on the bottom, and he picked it so that the lighter ones are on the bottom, heavy ones on the top. It was like he lost his 100% diploma on that one. So I'll always remember that one. Anyways. Okay, solvent extraction is next. Do you guys know, I don't have it with me, do you guys know what Italian salad dressing looks like? Ever had that? Okay. Italian salad dressing has 2 immiscible parts to it. There's the oily part and the water part to it. And you kind of have to like shake it up to have it like fully come together. That's basically how solvent extraction works. I think this photo kind of helps here. Imagine that you have some crude oil, but the crude oil is like mixed in with other stuff. The most common example we have is something called bitumen, B-I-T-U-M-E-N. These are called the oil sands. Everybody ever heard that phrase before, oil sands? Basically what happens is literally sand is mixed in with oil. Okay, oil part good, sand part bad. How do we get rid of the sand? Here's kind of the picture. What you have is this organic solvent where you really have like 2 things stuck together here, say oil and sand. And what you do is you add 2 different solvents. One is like, say, a watery-based one. One is an organic-based one, and they would really be separated into layers like your Italian salad dressing would be. Then you shake it up, right? So you mix your salad dressing and you shake it all up, and now it should all have an even consistency. But what you're hoping for is that, like, the sand maybe gets dissolved by the water, and the oil particles settle, and hopefully they separate a little bit due to gravity. That's called solvent extraction. Basically using different solubilities to change things. You guys remember the word solubility, right? There are certain things that dissolve and certain things that don't. And so if you can find some sort of way to like separate them based on this, that's solvent extraction. So we use this a lot on the oil sands, also known as the bitumen. Okay, so hypothetically, now as a oil company, you've now found some oil in the ground and you've separated it out so that you have a useful component. You still need to perhaps do some chemistry to it, and this is one of the reasons why Calgary and Edmonton have a lot of jobs in the chemical field. So if any of you guys actually do eventually want to go into the chemistry field, I know I had one friend in university, he worked for Shell, like the gas company. He worked for them in Calgary, although he was actually on their management side. But like, you could have a job as an engineer, and it's your job then to take those chemicals and to create something with them, to like refine them would be the term. Does that make sense? So these next couple of things here are all about equations and things we do to refine them. The first one is something called cracking, and I got 3 different examples. Okay. So here's a molecule. This is decane. Decane has 10 carbons, 22 hydrogens. So you finally found a way to break off a large chunk of material. Again, if you use my Lego analogy, Kinsey's now made a very, very long, big, just a big tower maybe, right? But say you don't want to have a big tower. Say you want a smaller piece. Well, what we've discovered is if you just heat something up, you can literally crack it. And by cracking, I mean like literally breaking it into pieces, right? So you used to have this long tower, and then you go, and you got two pieces here. And so here's the idea. What would really happen is that like this last little bit right here, oh, hang on, I gotta fix that. This last little bit right here, what you're gonna do is you're gonna crack it right there. You're gonna break that off. But in order to break that off, one thing's gonna happen. See how what's sitting right here? That would be an octane, but I got a problem. This octane right here does not have an end cap anymore because you've ripped this carbon off, right? So what ends up happening is, say, like one of these hydrogens right here ends up going and taking that last spot right there and filling in that spot, which means what you're left with is 2 carbons, and it would have been 5 hydrogens, but now it's 4 hydrogens. But what does that mean about its chemistry then? Well, rather than being a single bond, you need to actually have it be a double bond, but now you've cracked off a smaller piece. Okay? And it's actually really easy to do this. All you have to do is heat these things up. Now we're talking like past their boiling points. So like these things will probably be in their gaseous phase when you do this, but if you really heat them, you can actually crack a molecule. So that's known as thermal cracking, where you just use heat to add to it. I got another picture here to kind of help show the idea. Here's hexane. And what you're going to do is you're going to rip off this last little bit right here. One of these hydrogens is somehow going to attach itself right there, and you get your double bond sitting right there. So can you guys kind of picture that? That's thermal cracking. Now, I don't know a ton about the next thing afterwards. It's called catalytic cracking. If I knew more, obviously I'd work in this industry. So here's what I was able to research on it. Catalytic cracking basically means use a catalyst. What do catalysts do? By doing what? Reducing the... Where are you getting your activation energy from in the first reaction? From heating it up. So if you use a catalyst, do you need to heat it up as much? Exactly. And so basically that's the main difference, is if you use a catalyst for catalytic cracking, if you put it all together, you lower the activation energy. The activation energy is occurring because you don't need to heat it quite as high, and so you can use lower temperatures. Okay. I have no idea what this is. I'd have to Google it more, but apparently they use a zeolite catalyst. That just sounds so cool, whatever zeolite is. Hey, Google, what is zeolite? I think I heard aluminum silicate, so probably AlSiO3, something like that. Anyways, you don't need to know this. From what I understand here, the basic idea, though, is that thermal cracking gives you shorter alkanes, whereas the catalytic cracking can give you branched alkanes, or maybe even some cyclos, or maybe even some aromatics. And so it just really depends on what you want as your products. Do you want to have like a little group of 2 carbon to get cracked off the end? Or would you like to crack off something that somehow goes into a circle? But I mean, what you guys need to know is that it uses a catalyst, and we've talked about catalysts before. I found this picture right here. I think that helps explain it. If you use thermal cracking, this was meant to be a diagram as to like what type of carbons you would crack off. And it looks like you crack off a lot of 2 carbons. A lot of ethanes would get cracked off. Does that make sense? But you could crack off like a single methane or maybe a propane, but for the most part, most of the things would be like what we just saw here. You take a long molecule and you crack off a group of 2. Okay. But if you use catalytic cracking, you actually end up taking off more things in the C3, C4, C5, C6 range. C6 being particular because what is a good C6 compound? Benzene. And if you can crack off a C6 benzene, now you can make things that are aromatic. So, anyways, that's the big differences. The last one is known as hydrocracking. And the way hydrocracking works is that you also add hydrogen as an extra additive. And I think I can explain that with these pictures I found here. I'm going to use the bottom picture here. Imagine you have this very, very large molecule right here. This is a C26H54. And what you want to do is you want to crack it off into 2 different pieces. But you don't want them to be small pieces. You actually want relatively large ones. What you do is you cleave this thing. I can remember where it breaks. So let's see. You need that one there, that one up there. Down, up, down, down. I think you're cracking it right here. Okay. But what you do is you add hydrogen. And by adding hydrogen, you know how it breaks right here? What you would have had is a carbon attached to a carbon, and it would have looked like this, and it just keeps going in both directions. And if you want to cut it right there, what would end up happening is this carbon would no longer have its fourth direction attached, right? And the other carbon will no longer have its fourth direction. But what if you add hydrogen gas? Well, what basically happens is you add a hydrogen right here, cap it off, add a hydrogen right here, cap it off, and now you've just split across two molecules. You don't even need a double bond. You just add one hydrogen to this piece, one hydrogen to this piece, and literally just rip it apart. Can you guys kind of visualize how that would work? Right? Big long tower, big strip in a row, cut it in half. But the problem is it wouldn't have enough bonds. So add one hydrogen to cap off that side, add one hydrogen to cap off this side, you're good to go. So I have seen a question on this, by the way, and it's on one of your quizzes. So you'll see it. So, how am I doing so far? I got to speed up because I promised you I'd leave some time, and I'm going way longer than I thought. Okay, another topic I need you guys to know is something called catalytic reforming. And it basically is like what the words would be. Catalytic, meaning you need to use a catalyst. Reforming is very specific, though. It's going to form benzene rings. And I've got a picture of one of these right here. Imagine you started with this molecule right here. If you underwent catalytic reforming, what you would ideally do is rip one hydrogen off of here, rip a hydrogen off of here, rip a hydrogen off of here, rip a hydrogen, actually no, you rip more than that. You would rip both hydrogens off of here, rip most of your hydrogens off of all of these pieces right here. And if you could rip a whole ton of hydrogens out, you can see that one of the byproducts is a whole bunch of hydrogen gas. But in the meantime, what's happened is now you've made yourself your benzene ring, which is kind of cool. So that's catalytic reforming. This one right here somehow seems to take the carbon that was outside of a pentagon and somehow manages to shove it inside the pentagon and make it into a benzene ring. But all I need you guys to know, in case it comes up, never seen it, but in case it does, catalytic reforming basically says take molecules, turn them into benzene. The best way of doing that is basically rip a ton of hydrogens out. Because you guys know how benzene is supposed to have 6 different attachment points, where there's only 6 hydrogens there? Well, these guys right here would have had more hydrogens sitting there, right? Based on the way that it bonds, you would have actually had a whole bunch of hydrogens right here. So pull a bunch of hydrogens off and turn it into a ring. Okay, a couple other terms I want you to know. The term hydrogenation. Hydrogenation, and by the way, just reference back to that first slide if you're wondering what I'm talking about. Hydrogenation is basically add hydrogen, hence the name hydrogenation. Okay, so it's really basic. Take an ethene right here. You guys remember the term unsaturated and saturated? This is considered unsaturated because it is not full of hydrogens yet. And all you do is you add some hydrogen gas and boom, now it's got as many hydrogens as it can handle. This molecule here would now be considered saturated because all of its bonds are now full. So this would be unsaturated, and this would now be saturated, and hydrogen just solves that problem. So that's hydrogenation. What do you think dehydrogenation is? Moving on. Yeah, just do the opposite, right? So that covers... What was that? Oh, well, hydrocracking, though, is where you take a molecule and you crack it into 2 pieces, and you cap both ends with hydrogen. Whereas this one right here, hydrogenation, is where you take like something with a double bond, and you add hydrogen to it. Which ones? In a way, yeah. Yeah. I mean, a lot of organic chemistry either involves the addition of hydrogen or the removal of hydrogen. And doesn't that kind of make sense, though, in that all we've talked about so far is carbon and hydrogen. It's not like we've talked about a lot of other things. I know we'll get there, and we use oxygen and nitrogen and stuff like that. But, I mean, yeah, either adding or removing hydrogen is a big part. So, here's another example here. So this would be dehydration. Now, we haven't talked about this functional group yet. This is an alcohol. We'll get to that sometime next week. But this is dehydration. And I mean, just like you think the word would be, dehydration, unwater a molecule. Right? Hydrate, water. So here you have something that could be turned into water. If you rip it off, you're dehydrating something. Same thing actually happens in this one right here. Um, there's this molecule that was right here. You pull this stuff off. I love how they drew this. They actually wrote a minus water. That was a really unique way of writing it. They wrote it that you had to subtract water off of it. So this would actually really fall into two categories. This one. This would be dehydration because you're removing a water, and you'd also call it catalytic reforming because what did you make? Benzene. Yeah. Things can be in more than one category. Okay, this is a process called alkylation. I'll write it out up top here. Alkylation. The way alkylation works is that what you're trying to do is actually add molecules together. And I'm pretty sure I have a question like this I found off an old diploma as well, where basically the idea is you take compound 1 and compound 2 and you shove them together somehow, but with the very specific purpose of making something that has a lot of branches on it. Okay? Sometimes it's very useful to have compounds that have many branches to them. And it's actually gasoline that's the best example. You guys know when you go fill up your tank with gas, usually there's about 3 different options. There's like the 87 octane number, the 89 octane number, and if you really, really want to like put nice gas in your car, you put in like the premium stuff. You know what I'm talking about here? Anybody ever wonder what the difference is? Does anybody know? It's actually very little. It actually has to do with the extra refining that's done to things. Octane is C8H18. And if you had just a straight 8 in a row branch, that's octane. But we don't usually burn that. Because the way it works is that things that burn better have more branches to them. So if I were to kind of draw out an octane here, 1, 2, 3, 4, 5, 6, 7, 8, that doesn't combust very nicely sometimes. If I were to, like, say, remove a couple of these carbons here and make like a branch here and a branch here, and maybe remove this one and make a branch here and remove this one and make an extra branch here. See how I've made it like branchier? It's not like all in a row. It kind of compacts the molecule too a bit because keep in mind, these are in 3 dimensions, right? So rather than it being all in one big long line, it's now sprouting out in arteries that go this way and that way. This is a very branchy molecule. This might be an octane number of like say 93 octane. Whereas a lower octane number has the exact same components. It still has 8 carbons and 18 hydrogens, but it just doesn't have quite as many branches to them. Does that make sense? There's a little blurb in your book on it. I'll point it out to you guys later. But that's basically the idea behind alkylation, is that alkylation is a process by which you try to create a molecule that has a lot of different like sub-branches. So rather than it being just one long string of things, it looks like this. Here was a molecule, and here was another molecule. And by adding them together, we managed to put together a molecule that has 1, 2, 3, 4, 5, 6, 7 carbons. This is basically a hexane because there's the 1, 2, 3, 4, 5, 6, 7. But is it actually hexane? No, it's actually a pentane because you've got your 5 in a row, and you've got a branch here, and you've got a branch here, right? But branchiness, as like a word, actually affects how well it combusts. And I'm going to finish our lesson, by the way, with combustion, but just as a general idea. So that's why the term alkylation comes in. It's where you intentionally try to make branchy molecules. Good? Cool. Okay, I think I actually covered almost all the words on here now that were on this first slide, because I also talked about octane number. So now I want to finish my lesson kind of starting at the beginning again, though. Yes, most hydrocarbons that are mined out of the ground, though, they are combusted. But one thing that really drives me crazy, and this is just my personal opinion, okay? Please don't make this like your own. But like, it drives me crazy whenever I hear an environmentalist say, all oil must stay in the ground. Because not all of it can stay in the ground. We use at least some of it for useful products. Pharmaceuticals would be one. I cannot understand someone who would argue we should leave it all in the ground, but then I'd say, but then that means that my kid, when they need Tylenol, couldn't have Tylenol. You get what I'm saying here? So, no, I'm not disagreeing that there's an environmental component here, but there is a large part of it, though, that is still combusting things. So because of this portion down here, I cannot agree with the word all, but yeah, pretty much everything in this area up here, we combust it. And there is an environmental factor that needs to be then considered. So I want to talk and finish on that. So you guys should know a little bit about combustion, right? Combustion of hydrocarbons involves taking a certain amount of carbon, a certain amount of hydrogen, and we don't know what molecule we're picking. And what does it take to combust something? What are the other reactants required? The other reactant required. Yep, we need oxygen, and it always makes carbon dioxide and water. Except I lied to you. I do this a lot. That's actually not true. That was a partial truth. Most of the time, that's what that produces. But that would be something known as complete combustion. If combustion happens cleanly, and this sounds kind of weird because you've probably heard over the last couple of years that carbon dioxide and even water vapor are pollutants in a way, depending on the person you talk to. But this would actually be the cleanest form of combustion, where it literally just gives off carbon dioxide gas and water vapor. And that's complete combustion. That's actually not true. That's not what always happens. Does anybody have a wood-burning fireplace? Imagine that you burn something in that wood-burning fireplace. When you're done, you need to have a chimney so that the gases can escape. But when you're finished, is the chimney box, is the wood box empty, or is there something left there? There's ashes left over. Does that make sense? Even if you have a fire outside. Does that make sense? I mean, according to this right here, if you start with some sort of hydrocarbon, if you produce two gases, wouldn't the implication be that when you're done, there should literally be nothing left? And yet I guarantee all of you guys have experience burning something and there's like some sort of charred remains left. That's because complete combustion didn't occur. What actually occurred was incomplete combustion. Now, we don't show you guys this until grade 12 just to keep things simple, but let me show you some slides on how incomplete combustion works. There's actually side reactions that take place. Your hydrocarbon will produce carbon dioxide and water, but a side reaction will take place where it also produces carbon monoxide. You guys know much about carbon monoxide? Yeah, it actually will suffocate you. It's actually very dangerous. So a lot of, if you have a wood-burning fireplace, you definitely should have a carbon monoxide detector. And honestly, most places are now being recommended to have them as well. But here's the one you guys are most familiar with. It'll also produce some carbon solid. And we give this another word sometimes. We would call this like the soot that's left over when you're done. And so combustion is actually not one reaction. It's probably three things happening at once. Some stuff is being burned and it produces carbon dioxide. But simultaneously, other hydrocarbons are producing carbon monoxide and others are producing just carbon soot. Does that make sense? And so it's actually more complicated than you think of. There's actually three reactions. This one, you'll notice that I did the exact same thing, right? I started with this one in all three of them, and three reactions are happening simultaneously. What you may end up having happen then is like 85% of it is this, 3% of it is this, and 12% is this, like some sort of breakdown, right? And really that determines how clean your combustion is, because the more of these you produce, that's really the less clean it happens to be. Well, that's why sometimes you need to have like there's like additives you can buy to like cleanse your gas tank. You ever seen those? Like I buy some for my diesel tank, like it's like a fuel cleaner type thing. You might even see commercials where like Petro-Canada or Shell like advertises that they have like clean fuel because like they put additives inside to try to help clean your fuel tank. But yeah. So I've got some pictures here to kind of help illustrate what I've talked about, and then I'll finally be done. This one longer than I wanted. Here's a carbon monoxide detector. Here's like the ashes that are left over. This is kind of what you're talking about here, right? Like the inside of your car would actually have some like buildup, some crap that's kind of built up inside of it. And I mean, you can actually even see the exhaust, right? What you might be seeing here somehow is some sort of like carbony exhalingness, right? You know, in the same way that like when someone smokes, you can actually see like the smoke vapors leaving it. So here's what I need you guys to know about this then. If you want to increase complete combustion, here's the key. You need more oxygen. More oxygen leads to a cleaner burning. And for those of you who have a wood-burning fireplace, I used to have one in the old house I lived in. Do you guys know like how, did anybody have a wood-burning fireplace? Okay, you know how there's probably like some sort of little damper thing on there that increases the oxygen flow? And like if you open it all the way up, oxygen comes in, the fire roars, right? But after you get your fire going for a while, if you want a nice slow burn, like at least on mine, I had just a little stick I'd push in. It would decrease the flow of oxygen, and then basically it would burn like a slower burn. You guys know what I'm talking about if you have one of those? Okay. Well, that basically what was happening then is you were creating a more dirty burn because you were producing more carbon monoxide and more carbon soot rather than producing carbon dioxide, which is fine. It burned at like a slower rate. That's all. Okay. So oxygen is the key to this. Increase the oxygen, you get more complete combustion. Oh, so here's my summary slide for this little bit here. Complete combustion would be your hydrocarbon and oxygen gas to produce this. But what really happens is this. You take a hard hydrocarbon, you add some oxygen, and you make some carbon monoxide, some carbon dioxide, and some water. And really, I know I wrote this as one equation, but really 3 equations are happening simultaneously. And the ratio depends on oxygen. Okay, so that's my lesson for the day. I really enjoy this one, and you can see I've changed things around a bit. I hope you guys learned something today. You're not going to use this very much on my test, and yet I think this is worth knowing. No, honestly, read more news, guys. It's going to impact your lives as you move into adulthood. It matters. The fact that Alberta is like actively like at war economically with British Columbia right now is something that like maybe read up on a little bit because it's big in the news. Pipelines are another really big topic. And hopefully I'm not trying to influence you how you think politically and stuff like that, but it's complex stuff. There's an environmental factor to consider, a political factor to consider. There's a societal factor to consider in terms of like what is best for society. Do we want to completely cut off fossil fuels entirely? Can everybody afford to do that? No. Like I said, I hate the statement leave all the oil in the ground because I want my daughters to have medication if they need it. So at least have enough oil to make medicine. All right, anyways. Any questions? Cool. Okay. Tomorrow we have a work day scheduled for you guys to be able to catch up on some stuff. And then Friday we're going to write a quiz. Okay. What I think I'm going to do though, if it's okay with you, can I give you guys the quiz sometime on Thursday? I'm not here Friday. I have a dentist appointment. You guys can take the quiz with you on Thursday. And then if you want to work on it before class on Friday, you can. Because this next section won't take you nearly as long to do, but you still probably won't finish in Friday on class. So you'll probably need more time. So I'll just give it to you guys, and you can just do it whenever you get time. Sound good? Cool. Okay, I'm done.